Good evening everyone, this is the second video in this lecture series of particle physics. In this video we will be talking about particles like uh, fermions and bosons. Okay, especially in this one we will be talking about fermions. Okay, so far we have been exploring bosons, right? So what are bosons? If you remember, bosons are what? Integral spin particles, isn't it? They are integral spin, like can be one or two or anything, right? Okay, like whatever we studied in the previous class, like all the mediating particles, the particles that are mediating some kind of interaction, mediating particles. Okay, just a second. Let me, yeah, mediating particles. Okay, all the mediating particles are bosons. What, which were the mediating particles again? Gluons. Okay, gluons were the mediating particles for what? Strong nuclear force. Strong nuclear force. Then W bosons. Okay, W and Z bosons. W plus minus Z0 or Z naught. These were the mediating particles for what? For weak interaction, weak nuclear interaction. Okay. Uh, then gamma photon was your mediating particle for EM interaction, electromagnetic interaction, and graviton was also there. So, but these are also what? These are also bosons. These are all bosons. Okay. These are not fermions. Okay. Fermions are different. Um, so now let's look at these particles. Okay, fermions, the stuff that things are made of. So the things, objects, whatever we see, everything is made of what? Fermions. Because fermions are the one, like the what? Basic building blocks, we can say. Okay, fermions. All right. So let's see. So all known matter, okay, all the known matter is made of spin half particles for fermions. Okay, everything fermions, and these fermions, what spin? These are spin half particles. Okay, fermions are what? Spin half particles. It can be half, it can be 3 by 2 also. Okay, spin half particles. Or we call it odd integer spin half. Okay, spin half particles. It can be 1 by 2, it can be 3 by 2. All right, it can be what? 1 by 2, it can be 3 by 2. All right, yeah. So this is your fermions. Fermions are what? Fermions have anti-commuting statistics. What do you mean by anti-commuting? You know what is anti-commuting? What is commuting? Or anti-symmetric? Okay, we can say it anti-symmetric also. No problem. What do we, for example, there is a wave function. For example, there is a fermion which has a wave function as psi 1 2. Okay, psi 1 2. All right. So if psi 1 2 is equal to minus of psi 2 1, psi 1 2 is equal to minus of what? Psi 2 1, then this particle is a fermion. Right, you can say this is anti-symmetric property. Okay, this is what? Anti-symmetric property. Anti-symmetric property. Anti-symmetric property. But bosons are the wave function of bosons are symmetric, isn't it? The wave function of bosons are symmetric in nature. For example, this is psi 1 2. For example, this is psi 1 2. So psi 1 2 will be equal to psi 2 1. Psi 1 2 is equal to psi 2 1. So this is your symmetric property of wave function. Alright, and bosons are symmetric in nature. Alright, yeah. Um, now suppose what? So what are the examples of fermions? Fermions example, most common examples are electrons or protons. Okay, electrons or protons are fermions, but there are different category. We will go through that. Electrons or protons. Okay, best known fermions. Um, electron was actually the first discovered fermion. That was first fermion to be discovered. That was in 1807. Okay, 1807. And nucleus was discovered when? It was nucleus was discovered in 1980. Sorry, 1910. Sorry, 1910. It was by what? Whom? Rutherford. Right? Rutherford discovered nucleus. Right. Yeah, but it was not until 1980, 1932 that what the nucleus was understood to be a composite object. Okay,
Antiparticle are the negative of that of its corresponding particle.
what does it mean? It was not until 1932, all right, that the nucleus was understood to be a composite object. That means what? Up to 1932, it was not confirmed that nucleus was made of like protons, neutrons, anyway, protons and neutrons. Okay, it was supposed to be a separate thing. They were thinking about it. Then came two more scientists. What? Their name is Uhlenberg, Uhlenbeck, and Goldschmidt. I don't know the pronunciation properly, but whatever. This is Goldschmidt. Okay, they postulated that electron had what? Electron had h cut by 2 spin. Okay, h cut by 2 spin. In order to properly account for what? Zeeman effect. Zeeman effect. What is Zeeman effect? This is a task for you. This is Zeeman effect comes on atomic and molecular physics. This is your task to study about Zeeman effect. Okay, so that you can have a more deep knowledge about it. We won't discuss Zeeman effect here. Then also what Stone-Gallagher experiment. These are two very important experiments. You have to study about the Stone-Gallagher experiment. Okay, this one is also for you homework. You can study about it and come later and comment in the comment section. Okay, so this meant that Schrodinger's wave equation could not be used to describe the behavior of electrons. Why? Because Schrodinger wave equation did not account the spin thing. It did not take the spin factor into account. Okay, did not it did not take the spin factor into account. But Zeeman effect and Stern-Gallagher experiment, they took the spin thing. Okay, so yeah. Then came Dirac or Dirac, whatever. Dirac or Dirac. In 1927, then came Dirac in 1927. Okay, what he did, he wrote down a relativistic wave equation. Okay, this comes under your relativistic quantum mechanics. Okay, relativistic. Dirac wrote down relativistic wave equation. All right, and sorry, what does that relativity wave equation say? It says that what he wrote down a relativistic wave equation that he required to be linear in what energy E and momentum P. Right? That is what? What does it mean? That is linear in the operator del by del t, and for P it is what? Del vector. Okay. This equation, what did this equation predict? What did this equation tell us? It predicted that a charged particle of minus E, okay, had a spin of h cut by 2, but it's another charged particle having the identical mass, having the same mass but opposite mass has what? Spin, um, like that was also h cut by 2. Just the charge was opposite but the mass was same and the spin was same. Okay, so these two are called what? Antiparticle of each other. That was derived from like predicted by Dirac's what relativistic wave equation. Okay, you will study that in relativistic quantum mechanics. So these are called antiparticles of each other. All right. Yeah. And see, this is your electron. Minus E means what? Minus E means your electron. Plus E means what? Plus E means your positron. Okay, it's not proton. Be careful about that. It's not proton. Yeah, we sometimes write charge of proton is plus E, but yeah, that's different. But here the mass of electron and positron are same. Mass of proton is different. Mass of proton is 1836 times the mass of electron. So they are not identical mass. All right. So we cannot say that what these are antiparticle of each other, because what do we call? How do we define antiparticles? Antiparticles means identical mass. Two particles which are identical, like masses are identical, means masses are same, but what? But the charges are different. Okay, charges are opposite to each other. Charges opposite. All right. Then only we call them what? Antiparticle. Okay. Yeah. So this was discovered by someone called Anderson. Anderson, whatever. Which Anderson? I don't know. Some Anderson. Okay. In 1933. All right. So everything was around that time. Okay, 1930s or the 1920s. Okay. So all this spin half or spin escorted by two, everything, they all obey what? Can you tell me? All obey Dirac's equation. Okay. All these things obey what? Dirac's equation is very important thing in high energy physics, like relativistic quantum mechanics. Okay, you really need to clear this off. Okay? Dirac's equation. You just adjust the mass and charge in the equation to describe the particle of interest. Okay. So each spinor particle has a corresponding antiparticle. Like every spinor particle has a what? Corresponding antiparticle. This is the Dirac equation right there. Alright. So this is also true for most bosons. Okay. Like this is true. We are studying about fermions, but this is also true for bosons. Okay. But for some bosons, like the photon being the best known example, photon gamma, photon or something. Okay. Yeah. The antiparticle is itself. The antiparticle of photon is actually itself. Okay, we cannot say because photon doesn't have charge, right? We cannot say negative photon or something, right? And in general, like all quantum numbers of an antiparticle are the negative of that one, of like of the original particle, except for its mass. Okay, mass remains unchanged. Mass is always constant for particle antiparticle where mass is same, but your charge will be vary. Like charge will be positive, negative. Okay, that is a property of antiparticles. Yeah, like if we see the experiments, as far as the experiment has indicated, like all spinor particles in the world come in two basic types. Okay, all the spinor particles spin half. If we see, can you tell me this one? Spinor particles are basically two types. Okay, they're what? One are leptons and quarks. These are the fundamental particles. Okay, basic, because we cannot break them. What do we mean by fundamental? What do we mean by fundamental? What do you mean by fundamental particles? Means the particles which are the least, like the minimum thing. Like we cannot break them. Cannot break these particles. Okay. Electron is a lepton. We cannot break electron anymore. We cannot show that electron is made of something. But proton, if you be thinking like a proton, what about proton? No, proton is made of quarks. Quarks. Proton is a baryon. Okay, baryon is made of three quarks. We'll study about that later. But electron is a lepton. Electron is not a baryon. Electron is not made of anything. So that's why electron comes out leptons. And leptons are what? Fundamental particles. Okay, because leptons are quarks cannot be divided anymore. That's why they are what? Fundamental particles. All right, is that clear? Yeah. Next, what? Um, yeah, we can also make a table of that. All right. Yeah. You can say here make a table like the kinds of matter leptons. Leptons, particles that like particle leptons experience what? Weak interaction. Okay, like they do not experience strong interaction. Those are called leptons. And your quarks, they experience, the ones that experience what? Strong interaction. Those are your quarks. Can you tell me why? Because if you see, quarks interact between them, among them, with what? With gluon. And we know gluon is a mediator for what? Strong interaction. So we can say that quarks like experience strong interactions. All right. Yeah. So what are the leptons? What are the different type of leptons? We'll see that now. Leptons. You can give a heading as leptons. See, I am giving it very conceptual and concept. This videos are very conceptual and in depth analysis. Okay, so but don't expect me to give you notes. Like I won't write like these are these in sentences. These are made like left to you to do. That's the that's the process. That should be the process. Like you study from a lecture and you make your own notes. If I give you the notes, then there is no purpose. Okay, you won't learn anything. You will just try to memorize those and write in the exam, and that won't help. That won't help in the entrance exam. Trust me. Yeah. So leptons. Leptons is what? So what are the leptons? Electron, lepton. We know an electron is a lepton. Electron, right? And along with the electron neutrino. Okay, electron neutrino. We write it as what? Like this. Okay, yeah. Next is your muon. Muon is a lepton. We write it like this. Mu, simply your mu. We can write a mu minus. Okay, and its neutrino will be mu neutrino. Every lepton has its neutrino. Okay, mu neutrino. We can write it as mu subscript e. Okay, and last one is tau or tau, whatever you can pronounce. Some people call it tau. I find it really weird to say tau, so I just say tau. So tau or tau neutrino, sorry, tau neutrino. All right, so these are your leptons, and all the leptons are what? They are antiparticles, isn't it? They have their antiparticles. Electrons antiparticle is what? Positron. I can say antiparticles. Electron has antiparticle as positive. Sorry, positron. Okay, positron has charge what? E plus, right? Electron neutrino antiparticle will be what? Electron antineutrino. That's it. Or positron neutrino, or we just say antineutrino. Okay, just say antineutrino. Just put an anti in the antiparticle for these neutrinos. Okay, anti mu neutrino, anti tau neutrino. That's it. Okay, yeah. Mu1, that would be mu anti mu1. There is no name for that. Tau, anti-tau. Okay, tau plus antiparticle of tau. Okay, anti-neutrino. We'll just put a bar over it. Okay, mu neutrino, put a bar over it, and tau neutrino, just put a bar over it. Right. So there is an interesting thing is lepton number. All the leptons have their lepton numbers. So lepton number of electron is plus one. Keep that in mind. Okay, lepton number of electron neutrino is plus one. But lepton number of positron is minus 1. You will find it really awkward because you'll be thinking this is E plus. So there should be no, the charge is plus 1. But lepton number is minus 1. Why? Because electron is the original lepton. So its antiparticle is positron. So antiparticles have the opposite like lepton number. Right? So this is minus 1. Same goes here. Mu1 has lepton number plus 1, but anti muon has lepton of -1. Exactly goes for tau and tau neutrino. All right. Then next is your quarks. Quarks are the another fundamental particles. All right. So quarks have some flavors. Okay. There are some flavors of quarks like u, up, down, this is d, up, down. Then what? Charm, strange, charm, strange. Okay. Charm, strange, and top, bottom. Top, T, bottom. Why the names are like this? That there is no why for it. It's just like this only. Okay. You can also ask like why quarks are called quarks. Okay, so no. Okay, so up, down, charm, strange, top, bottom. The charges are see the charge of quark is what uh, up quarks are charged plus 2 by 3 e, okay, and down quark like the negative ones are charged minus 1 by 3. Okay, this is the thing about it. So this is what plus 2 by 3. So I can write it as plus 2 by 3 e charges I have written in the up. See up charm top minus 1 by 3 e we have written in the down part. Okay, down strange bottom. All right. Yeah. So these are your like lepton and quarks. They have the other things also like antibody, anti-op, anti-down. How do we write it? Anti-op or antibody op U dash, down D dash. Yeah, like that. Okay. So what do you mean by flavor? These are called the flavors of quark. Okay. And the study of like there's another thing called color of quarks. Okay. Study of color of quarks is called quantum chromodynamics. Okay, that is another thing. Flavor of quarks. Okay. So the quantity flavor is actually what? The charge experienced by the weak interactions. Okay. So we'll see that a strong interaction has the effect of changing a quark of one color. So the color of quarks is red, green, and blue. It doesn't mean the color exact the like literal color. No, it's a different one. That one we will see in the next lecture. That's a whole different thing to understand. Okay, red, green, and blue. These are the colors, color component like color. This color is not your actual color like the sky is blue, not like that. Okay, yeah. So yeah, so this is your like fundamental particles, leptons and quarks. All right. So read about them. Go to internet, read more about them. Read the properties of leptons. What can they do? Why? Like read everything that comes with the question why. Okay, because in interviews you will get questions as why this, why that. Okay, so you must be able to answer them, right? Yeah. So this is overall a brief like lecture on fermions. Okay, basically we studied about fermions in this class, like the fundamental particles. Okay, the particles that the objects are the real objects are made of. Okay, yeah, that's it for today. Uh, we'll continue this. We will have the next lecture on the color quarks. Okay, red, green, and blue. Thank you very much.